So how in the world do we know what stars billions of miles away are made of? Well, the secret is actually hidden in plain sight. It's in their light. Turns out, every single atom in the universe, when it gets energized, gives off its own unique pattern of light. It's like a secret code, a cosmic signature. So the real question is, how do we crack it? Let's dive in. This unique pattern is called a spectrum. And what's so wild is that this isn't some random splash of color. No, it's a series of sharp, super distinct lines. Each element has its own set, and it's a fundamental property, as unique as its own name. This is what lets us identify what something is made of, just by looking at the light it spits out. And that right there is the perfect analogy for all of this. These spectral patterns are literally the fingerprints of the elements. You know how no two people have the same fingerprint? Well, no two elements have the same spectrum. It's our universal ID system, whether we're looking at something in a lab right here on Earth or a galaxy millions of light years away. I mean, just look at the difference here. On the left, you've got the pretty simple fingerprint for hydrogen, and on the right, the much more complicated pattern for helium. This immediately brings up the big question, why? Why are they different? Where do these specific individual lines even come from? To get to the bottom of that mystery, we've got to go inside the atom. And we're going to start with the simplest one of all, hydrogen. Just one proton, one electron. You see, if we can understand how hydrogen works, we unlock the basic rules for, well, everything else. Okay, so here's the absolute key to the whole thing. Inside an atom, an electron can't just hang out wherever it wants. Its energy is quantized. The best way to think about it is like a ladder. An electron can be on the first rung, or the second, or the third, but it can never, ever exist in the empty space between the rungs. It's a really weird, but fundamental rule of the quantum world. And to keep it all straight, we just label these rungs with numbers. We start with n equals 1 for the bottom rung. That's the lowest energy level, closest to the nucleus. As we go up, n equals 2, n equals 3, and so on, the electron has more energy, and it's further away from the center. It's a surprisingly neat and tidy system. Right, so we've got our ladder of energy levels all set up. Now, what's the actual action that creates the light we're trying to decode? It's something called a quantum leap, and this is where the magic really happens. Here's how it goes down. First, imagine an electron just sitting on a high rung, let's say n equals 3. Then, it spontaneously falls to a lower one, like n equals 2. As it falls, it's got to get rid of that extra energy somehow. And it does that by spitting out a single particle of light, a photon. And this is the crucial part. The size of that drop, that fall, determines the photon's exact energy, which we see as one specific color. And get this, the whole process works in reverse too. When an electron falls, it emits light, creating those bright colored lines we saw earlier. But an electron can also absorb a photon of the exact right energy to jump up the ladder. When that happens, that color of light just vanishes from the background, and that creates a dark line. It's really just two sides of the exact same coin. Now, this isn't just some cool abstract idea. Physicists figured out that we can actually predict these lines with mind-blowing precision. There's a formula that lets us crack the code of an atom's light completely. So that leads to a huge question, right? Can we actually sit down and calculate the exact color? Or, to be more scientific, the exact wavelength of the light that's created when an electron makes any given leap? And the answer is a huge, resounding yes. It's all thanks to this, the Rydberg formula. Now, don't let the math scare you. This isn't just a bunch of symbols. It's the instruction manual for our electron's ladder. Let's break down what it all means. Okay, let's pull this apart. Lambda there, that's the wavelength. That's the color we're trying to find. R is just a special number that physicists figured out, a constant. Z is the atomic number, so for hydrogen, it's just 1. And here's the best part. N1 and N2, those are just the rungs on our ladder. N2 is the higher rung where the electron starts, and N1 is the lower rung where it lands. That's it. You just plug in the start and end rungs, and you can predict the color. What's really incredible is that all the possible jumps an electron can make, they actually group together into these neat little families, or series, and it all depends on which rung the electron lands on. If it lands on the bottom rung, n equals 1, we call that the Lyman series, and it emits ultraviolet light. If it lands on n equals 3 or n equals 4, that's the Paschen or bracket series, which give off infrared light. But take a look at the one in the middle. Just one. That's it. Out of all the possible leaps and falls an electron can make in a hydrogen atom, the only ones that produce light we can actually see with our own eyes are the ones that land on that second rung, n equals 2. This is called the Balmer series. All the other light, the UV, the infrared, it's completely invisible to us. We're only seeing this one tiny, specific window into what the atom is doing. Alright, so quick pop quiz for you. If an electron jumps from the fourth rung, n equals 4, down to n equals 2, which series does that light belong to? Well, since it landed on the second rung, it's gotta be part of the visible Balmer series. Simple as that. Now, here's the really beautiful thing about physics. These rules, this ladder, this formula, it doesn't just work for hydrogen. It applies to a whole family of other atoms that behave in a really similar way. And this gives us even more power to decode the universe. So, what are these hydrogen-like atoms? The rule is incredibly simple. It's any atom or ion that's been stripped down so it only has one single electron orbiting it. Think of a helium atom that lost one electron, or a lithium atom that lost two. They all have more protons in their nucleus than hydrogen does, but they share that one crucial feature, just a single electron. And because they all have that same one electron setup, they produce the exact same pattern of spectral lines. But, and this is a big but, remember that letter Z in our formula? The extra protons in the nucleus mean a stronger electrical pull. That makes all the energy jumps bigger, and a bigger jump means a shorter, bluer wavelength of light. The formula tells us exactly by how much, too. The shift is proportional to Z squared. Okay, let's put that to the test. A helium ion has an atomic number, Z, of 2. So how much shorter will its wavelengths be compared to plain old hydrogen? Well, the formula uses Z squared, so 2 squared is 4. Its wavelengths would be 4 times shorter. It's a simple rule, but man, is it a powerful one. Wow, okay, we have covered a lot of ground here, from quantum ladders all the way to cosmic fingerprints. So let's take a second and just boil it all down to the key takeaways. Alright, so to wrap it all up, every atom has a unique fingerprint made of these discrete lines of light. Those lines are created by electrons jumping down between the fixed rungs of their energy ladder. The bigger the jump down, the shorter and bluer the light it spits out. We can predict these lines perfectly using the Rydberg formula. And for a simple hydrogen atom, the only set of jumps our eyes can actually see is the Balmer series. And that brings us right back to where we started. If every atom has a fingerprint that it imprints onto every photon of light it touches, just think for a second about what that means. What can the faint, ancient light from a star, or a nebula, or a galaxy far, far away tell us about what the universe is made of, about its motion, its temperature, its history? It turns out, everything. It's all written there, in the code of light.